Okay, so yeah, this is X is a random variable with exponential distribution with some parameter, and Z is a normal random variable with zero mean and unit variance. And assume that X and Z are independent. Compute E of Z given root of X by 2, right? So whenever there you see like E of Z given X, right? By the way, I doubt if it is Z divided by X or Z given X. So I'm giving this problem in the context of Z given X. Right? So Z and X are independent. So any function of X will be independent from Z. Okay. So that means this is nothing but E of Z only, right? So E of Z is nothing but 0 mean. Okay, so I just wrote down this since Z and X are independent. So any function of X will be independent from Z. So that's why E of Z is 0 as Z is distributed normal 0 to 1. Okay, so yeah, this is a simple one. Second is also of the same thing, like X and Y are uniformly distributed, IID random variables, but between 2 and 3. We want to find E of X given Y. Again, I was just not sure if it is E of X given Y or X divided by Y, so I try to do both for this case. Right. So if they are, if you want this conditional expectation of E of X given Y, since again X and Y are independent, there is nothing but E of X, that is nothing but 2.5. Right. So now consider other case. So you want to divide. So Z is nothing but the division of X and Y. Right. In that case, we want the expectation of this thing, Z. To see the range that Z can take is nothing but 2 by 3 to 3 by 2. Is that clear? Because, yeah, cool, right? 2 by 3 to 3 by 2. And now, so I think in the last week, we tried to do this manipulating multiple random variables. So anyways, I thought for the completion, we do it properly at this time. So we can put Z as X given Y and W as Y. And so we want the distribution of Z and this density of Z. This distribution will get density. If it is continuous, we can differentiate. So that's it. So you get the inverse transform. Not by transform, I mean inverse representation of X and Y in terms of Z and W. Right? So you have X is nothing but Z and W, Y is equal to W. Right? So W goes from 2 to 3. So this is what I was saying last time, right? So you, whenever you have this invertible transformation from ZW to XY, right? So you can do the representation, the transformation through this Jacobian, right? So FZW is equal to your true input variables times the Jacobian evaluated at this values of X and Y. So here X is ZW, Y is W. We can view this as the solution of X, Y in terms of Z and W. Okay. So you will be able to use only when this transformation is invertible. Otherwise, this is not feasible. Okay, so that's it. Jacobian is given like this. You evaluate it, and this is mod. This is determinant, and you will get this is mod W. Since W is positive, right? 2 to 3. Just throw away this mod. Right. Again, you have to integrate with respect to W. This density you have to integrate with respect to W to get as a function of Z. Right. Since you know the W goes from 2 by Z to 3 by Z. Right. So you integrate this from 2 by Z to 3 by Z. Okay. So what do we get? This is nothing but w square by 2. So this is 5 by 2 times z square. I mean 9 by z square minus 4 by z square. It gets to that is 5 by z square. Okay, so the range is important. As I said, the range goes from 2 by 3 to 3 by 2. Why the range is important? We want to calculate the value of z finally. So that is nothing but we do this 5 by z times this z into 1 by z square, and that is 1 by z, 2 by 3 to 3 by 2. And this is nothing but 5 times log 3 by 2. Okay, this is clear. Yeah, this is important, this thing, and identifying the range of z. Can go to other question. That is clear. Okay, so so I think I've done this first. Yeah. So you are given a conditional density, something like this. The question is here, right? Yeah. This is a conditional density, and mind you, this is a density because it integrates to 1 and this positive. Um, so basically, it is uniform between 0 to x for any given x. And you are asked to evaluate the moment of kth moment of y and the variable y given x. It is very simple because you are given the desired density also. So just substitute it, and yeah, you get this. Yeah, I think this should also be fine. Okay. And yeah, even this should be straightforward, but anyway. So this is the question: the joint distribution of x and y. I mean, it should be density, right? Is given like this, and you want e of y given x. Right. So yeah. So y given x, we want, so we have f of x comma y, we want fx of x. So for getting fx of x, we just integrate y because x and y are going 0 to infinity. We just integrate with respect to y to get fx of x. What you are integrating with respect to y? The f of x comma y, right? So yeah, when you integrate it and simplify, you end up getting 1 by 1 plus x whole square. Okay, so how do you get f of y given x? Is this quantity divided by this quantity. 1 by 1 plus x square goes, and you are remain with 1 plus x whole square. Right? On this density, conditional density, you want to have the expectation p of y, right? So ideally, there should be y here. I mean, that I get here. So I just missed a y here in this line. Right? Y times y. So again, by change of variables, you end up getting 2 into 1 plus x. So remember, this integral evaluates to 2. By conditional expectation. Let's see. Calculate the conditional expectation with conditional density. Uh, You can compute expectation with respect to distribution also. Uh, so yeah, you can compute this with respect to distribution also. Basically, um, if you are given a distribution, say x is positive and positive random variable, and if you are given a distribution, so you take the complementary of the distribution. Complementary means 1 minus that, and find the area under curve. Area under the curve. So that is nothing but expectation. I mean, you can show that that is a expectation, and you can give a try on that. Show that the area under complementary CDF is nothing but the expectation. Assume that this is a continuous random variable and it is always positive. Maybe next time I can show that. Yeah, with distribution also you can do that. There is a different way of computing. Okay. Yeah, so here is where there is some difficulty starts. Um, the question here is this we have covered. Yeah, we have two-dimensional random variable joint PDF like this. This is f of x comma y is varying as a function of y as it looks, but it's not. It depends on the values of x as well. So because it is defined in this region. So if you take the right half of the plane, right, and so and the desired region is above the 45 degrees, right? So in only in that region it is defined as e per minus 1. In that sense, it is a function of x. Okay, so that's not the question. So what we want is what is the regression of y on x? So here the regression of y on x is nothing but you want to approximate the random variable y by some linear combination of x. The linear combination, I mean some constant times x plus some shift b. So y is equal to ax plus b, right? Because y is not equal to ax plus b. You want to approximate y with ax plus b. Right? Now, to once you do some approximation, right? So you want to have a measure on error, right? How good y is approximating with respect to this a times x plus b, right? So you minimize this y minus ax plus b whole square, and you minimize with respect to a and b. So that is called as regression of y on x. Okay, and right. So you want to approximate this y by ax plus b equal to is just abuse of notation here, right? So you can assume this is y hat, right? Y hat is ax plus b, and you are minimizing y and y hat by choosing a and b appropriately. So if you do a mean square error minimization and differentiate with respect to a and b, right, you get this is the as the solution. Okay, so b is nothing but e of y minus a times e of x, and a is nothing but covariance of x comma y by your variance of x. Clear? So I mean, for this question, this is assumed to be you have to know this. Otherwise, it's we cannot do this question. Okay. Um, right. So to compute, so what are the things we need here? We need a joint density of xy because we need covariance of xy. And to get e of y, we need f of y, and to get e of x, you need f of x, right? And yeah, that's it. That's pretty much. So fy of y, just integrate with respect to y. I mean, integrate out with respect to x, and x goes from 0 to y. That you get as y times e power minus 1. And fx of x, same thing, but x here now going from, sorry, y here integrate with respect to y goes from x to infinity. That is nothing but e power minus x. Okay, and now e of y is 2, right? And you can check that it is 2. And e of x, it is 1, and variance of x is 1 because this is exponentially distributed. And this is gamma distribution. Okay, gamma distribution with parameter 2. So that's why this expectation is 2. Okay, so now we have f of xy, we have f of y, f of x, and we have all the ingredients. Let's compute e of xy. All right. So a of xy, by definition, you have this, and see I've just written down why these integrals are going from 0 to y and y to infinity. So this region 0 is less than x is less than y, right? So this is this upper triangle, right? The entire this thing, right? Upper half of the 45 degree. And in this line, to cover the entire region, you can go from x. You can assume x is going from 0 for a particular value of y, but then y itself goes from 0 to infinity, right? So y goes from 0 to infinity, and at any point x goes from 0 to y, right? So that's how we integrate that region, integrate out that desired region, basically, right? So yeah, let's say you just substitute f of x comma y as e power minus y and integrate this region out. And here again, we get this gamma integral, the gamma density, or gamma function to be precise, not density. Right, so this is what we get if you integrate it out. Right, so this is nothing but half goes out, y cube e power minus y. Right, so e power minus y, you can write it as y power 4 minus 1 because it is 3, y and y cube is 3. So in general form of gamma density is gamma function is this gamma of n. N is say any positive thing, right? Uh, can you hear me now? Okay. Yeah. So gamma of n, any integral, is defined as 0 to infinity. Say e power minus y to the power of n minus 1 and dy. Right? You integrate out with respect to dy. And that n, the gamma of n is nothing but n minus 1 factorial. Okay, so this is nothing but 3 factorial. So there is 3 into 2, but then you have this 2 here, and that's why it is 3. I mean, this integral is also straightforward. So you can, this is nothing but e power minus y, so you can pull out y from x, but then x is going from 0 to y. So this is x squared by 2, y squared by 2. I mean, because there is an x and y here, right? So that y is here. I forgot to put that y here. Yeah, that's why you get a y cube term. This is clear, right? Why we got 3? If not, I can once again just go over this. Regression, not really. Not really. Not really. But what makes you think that I want to know? Maybe there was some context to it. Maybe I am not sure if the mean square error conditioned on any given x has connection to it or not. Maybe it might have some context to it. But yeah, for this problem, you don't need it. Right? You just need covariance and variance of x. And yeah, so that's it, right? So covariance of x y is nothing but 3 minus 2. Why it is 3 minus 2? Because e of x y is 3, e of x is 1, e of y is 2. And that's why 3 minus 2 is 1. And b is nothing but, sorry, a is nothing but this 3 minus 2 divided by variance of x. Variance of x was 1 because it was exponential random variable. And b is nothing but a minus, what was b? Yeah, e of y minus 3 times e of x. Right? 2 minus a was 1 and e of x is 1. B is also 1. So y is equal to 1 plus x. Okay, so now we are asked to evaluate variance of y given x. Here you need the conditional density. Right? So e of y given x, you just get f of y given x like this. And then e of y given x is again evaluate this integral. E of y square given x, evaluate this integral y square times the conditional density. Then you just have to do this m2 minus m1 square. And that gives you the variance. Yeah, we can move to next question if this is clear. Okay. So now we are given an exponential random variable. Okay. I mean, by now you should be able to figure out that it is a distribution function of exponential random, right? And mean is nothing but 1 by 0.04. Right now we want the expectation of the exponential random variable conditioned on the x itself, that x takes at least t. Right, to evaluate this again, right, we need small fx of x greater than t. Okay, so to get small fx, we need capital F and then differentiate to get the small f. Again, right, we go to event the definition of the conditional probability. Right, so probability, this is nothing but probability x less than or equal to x given x greater than t. when you expand that conditional probability, you end up getting this, right? So this is nothing but um, uh, integral of t to x small f divided by probability x greater than t. So this is nothing but this thing, right? Here you use the fact that fx of x is 1 minus e power minus lambda x for exponential distribution, right? So this is when you use that, you get this thing, e power minus lambda t minus e power minus lambda x by e power minus lambda t. Why do you get this thing? Is because probability x greater than or equal to t for exponential distribution is exactly same as e power minus lambda t, right? By the way, lambda is 0.04. I just abstracted it out for simplicity. So this is it, right? This is the distribution function of x conditioned on x greater than t, and density is nothing but this. Okay, so what is the expectation? Expectation is you have to integrate under this probability distribution. Okay, that is lambda over e power minus lambda t. X goes from t to infinity, and x e power minus lambda x. Right. So we will plug in this multiplication later. We just let's see this here in evaluating this integral by parts. Right. So u integral v, and yeah. So this goes from t to infinity, and um, yeah, I think I made some typo here and corrected in the second line. This is nothing but the second part is nothing but minus times you differentiate the first integral and take the second integral and keep it under the entire this thing, right? So that's what it is. So minus times you differentiate x, that is 1, and you do the integral of this e power minus lambda by minus lambda, and you evaluate the entire, right? X goes from t to infinity. Substitute this t and the limits here, you get this term, and yeah, and finally again you integrate this e power minus lambda x by minus lambda with respect to x, you get this term, right? This term, right? Minus is there, minus lambda was got because you took integral. Again, when you take the integral, it will become this minus lambda equals lambda square, and substitute the limits from t to infinity, and yeah, that will give you this term. But then you have to multiply it with lambda by e power minus lambda. So that will give you t plus 1 over lambda. Clear? I mean, it's very simple. I mean, just manipulating this integration by parts carefully. So yeah. Um, and yeah, let's come to the interesting part today. Here we are given x1 to x5 are ID uniform random variables. Okay, they can take any values from 0 to 1 randomly, and I want the probability that x1 is the smallest of them and x5 is the largest of them. So by symmetry, right? How many of these things are possible? How many for any given realizations of this question is this thing? X1 to x5 are ID and drawn from 0 to 1 uniform random variables. right? And we want the probability that one of them, that is x1, is the smallest, and one of them is the highest. So there is no preference for x1 or x5. You can pick them anything. X3 is smallest and x5 largest, right? Okay. So here, so by symmetry, we have these things, right? You can have five factorial possible arrangements of this random variables, and any of them, and any of them is equally likely of this all five factorial arrangements, right? And now what we want is um, so here the desired event is this thing. I want x1 to be smallest, and I want x5 to be the highest, right? And I want this three random variables are free anywhere in between, right? So such that they are greater than x1 and less than x5. So you have three factorial possibilities here. They can themselves permute among themselves. But yes, this is greater than x1, this is less than x5. Right, so your total desired events are this 5 factorial is the total number of arrangements, and then 3 factorial is this thing. Okay. I know it is a bit confusing, but yeah, you can take some time to do this. I'll figure out a proper, axiomatic way of what change will have to do. What is the same? Identical but not independent. Hmm. So basically, you that this factorial argument itself arises from the fact that they are identical. Otherwise, right? Probably we may have to go by first principle in the sense that since you want x1 to be the minimum, right? Um, so you may want to write this as probability x1 less than or equal to x2. And probability x1 less than x3 and probability x1 less than x4. Okay. Again, because x5 has to be the maximum, right? You may want to write this as um, right again, like x5 is greater than x2, x5 is greater than x3, x5 is greater than x4. So you may want to find the this joint intersection probability. Let's say probably next time I try to pull out if they are not identical, right? Independent and not identical. see what expression they come out. But yeah, these arguments you can put big just because they are right. Okay, so here is another question. X1 to Xn are ideally distributed, any random variable. Then we want the distribution of the max, right? This is the question. So what, by definition of distribution, this is probability z less than equal to z is the event you want. Suppose this has happened, right? Z is less than or equal to z. Z is nothing but by definition maximum of the n variables. So the maximum of n random variables is less than z. That means each one has to be less than z. Right? So far, no assumption has been made on ID or whatever. Right? So far, this is generic till this point. Okay, and because they are independent, right? You can write like this. All the events are independent. Why they are independent? That is the assumption. Right? So this is nothing but fx of z raised power n. Why this is fx of z raised power n? Because x1, x2, x3 they all have common distribution capital fx of z. Is that clear? Why uh, this thing has come and why this thing has come, and of course this also. Yes, so small f is nothing but you are the density is nothing but you differentiate your distribution. Okay, so that's it. So here is another question. You want to find the minimum of the n random variables. Same x1 to xn, some CDF or density they have. Right? We want to find minimum. So the trick here is you cannot, if minimum is less than something, then any of the possibilities is equally likely. Right? That doesn't give you the information, right? So what I meant by that is if you have say 1, 2, 3 and minimum, let's say if that is less than say 0.5. So not 0.5, say 1.5. Right, so that doesn't give you any other information on the other. So here we resort to the this complement of your distribution, that is 1 minus probability z greater than z. Right, so what happens if minimum is more than something? If minimum itself is more than something, everything else has to be more than that. Right, so the same thing, right? You cannot directly use this. So you use this 1 minus probability z greater than z. And probability z greater than z is nothing but minimum of this greater than z. But then it factorizes into each of these individual random variables. Right? So this is equal to probability x1 greater than z whole power n. Why? Because x1, x2, xn they have same density. Okay, and that is nothing but this probability x1 greater than z is nothing but 1 minus fx of z. Right? 1 minus fx of z. And that's it. So probability z less than z is what you want. This is what you want. and this is 1 minus probability z greater than z. Probability z greater than z is nothing but 1 minus fx of z whole power n, right? So 1 minus fx of z whole power n. So yeah, this is the distribution of minimum. This is another continuation, but anyways, you're clear about this thing, right? Which one you want me to explain again? One minus probability z greater than z. This is by definition, right? This is by definition, right? Z can be either less than z or greater than z. So when you sum that, that is 1. So that's why probability z less than z is 1 minus probability z greater than z. Okay, so we want me to expand this part. This part. Okay, so this is nothing but the probability x1 greater than z is nothing but 1 minus probability x1 less than or equal to z. By definition, this is a CDF, right? Probability x1 less than or equal to z is nothing but fx of z. So this is 1 minus fx of z. I should have written 1 minus fx of z here. Okay, so that is nothing but substitute 1 minus fx of z here, and that's it. 1 minus fx of z whole power. Clear, right? So yeah, now we move to more generic thing. You know, the x1 to xn are random variables. X1, let's denote this as the least random variable. Xn is the highest random variable. I'm just denoting these things in the bracket. This is x of x subscript of 1 under in brackets is not same as x1. Okay, that's a, I just want to emphasize that. And x of n denotes the maximum of all the 1 to n random x1 to xn. And x of k denotes the kth minimum. Kth minimum in the sense x1 denotes the least, x2 denotes the second, uh, what should I say? Second least, and x3 denotes the third least, like that. Clear, right? Yeah, so we want the distribution of xk. Xk is the kth least. Okay, so this is the generic form of this order statistics, right? So fxk of x is the event probability x subscript k less than or equal to x. So since x subscript k is defined to be the kth minimum, right? So this is nothing but if the kth minimum is less than some value x, definitely k of them will be less than x, right? So the desired event is at least k of them can be less than x. So this x subscript k is the kth minimum. That means if the kth minimum is less than x, by definition of the kth minimum, at least k values should be less than x. Definitely k values will be less than x. So x1 is the least. So x of 2 is the least, x of 3 is the least. So if f of x of 3 is less than some x, definitely x2 and x1 will be definitely less than that, because by that's how they are defined, right? Okay. So because these are all independent and identically distributed, it's like binomial thing, right? At least probability of at least k of them, you know, event of desired event is at least k of them satisfying this condition, right? Xk less than x, k of the n random variables less than x. At least is nothing but you can choose n choose k probability x less than or equal to x whole power k times, there's a typo, 1 minus fx of x whole power n minus k. There's a typo here. It should be 1 minus fx of x whole power n minus k. Okay, so why do we get this thing n choose k? Because those k can come from anywhere out of n. How binomial like time term appear? Okay, that's what I was saying. So basically, this is like at least k of them. Okay. Now let's bother only about k. K plus one, so on, n can happen, right? That's what it is. So let's worry only about k. We have at least definitely we want to know k out of n random variables is less than x. So it is like this. Uh, uh, Let me give you an example. Uh, so you tossed 10 coins and you go and you want the probability of obtaining two heads. Two heads, and you just tossed 10 coins. So how many ways you get two heads? Those two heads can happen at anywhere from 1 to 10. So that is nothing but you choose any two slots out of 10 and you put head in that slots. Now, how can you choose two slots? It's nothing but 10 choose 2. Got it? Here also you want at least k of the n random variables to be less than x. So sorry, I wanted to say exactly k of them can be less than x. So that's what that means. X1 to xk can be less than x. No, x1 can be less than x. X4 can be less than x, and so on. It's like distributing n to powers of a and b. Yeah. I mean, you can think of distributing powers of n to a and b, but I did not understand your thought process of linking that distribution of n to a and b and here and what we are discussing. But you're following what I'm trying to say. You can correlate this with whatever I had toss example I gave you, right? You're doing a coin toss, and out of 10 tosses, you want what is the probability of getting two heads? Now, those two heads link to K. Getting head, you can assume getting head is as an event less than or equal to X here, and there are n of them. N of the tosses happen, and you want the toss for which this is satisfying, xk less than or equal to x. I mean less than or equal to x. Yeah. So I kept this thing as I said last week, right? We will do some more interesting stuff. So yeah, we have two more interesting problems of similar kind. So yeah, this may be a bit, but yeah, let's do it because anyways, we can go over this thing next week also. Uh, let's clear out this doubt next week. Okay, but the pay the attention to these arguments, right? The correlation with that example that I gave, right? So this is the event. K of them should be less than x as an event, desired event, and k is at least k here. So k goes from k to n at max. Okay, so you are tossing a fair coin repeatedly, okay, and you stop this game only when you see two consecutive heads. You got the question? You keep tossing a coin, and you stop the game when you see two consecutive heads. Game is stopped when you get two consecutive heads. Okay, now the question is what on an average how many tosses I need to get the two consecutive hits. I mean, on an average, after how many tosses the game is stopped. If you want to use question in another way, right? Question is clear, right? Right. So this kind of problems are typically solved by conditioning on the first toss, depending upon the question, conditioning on the last toss. Right. Um, whichever is convenient. Because you have only two tosses here, it's makes sense to condition on the first toss. So let's say you condition it on the first toss, right? and see if first toss is head, right? So how many tosses on an average you need? So you need, if first toss is head and second toss is also head, let us say, and head is happening with probability P. And if second toss is also head, game is done. By two tosses, you're done. Because you got two heads. And that happens with the probability P. The second toss, you get head with probability P. And yeah, even before that, I have denoted E of Z as the expected tosses to get two consecutive hits. Right? This is what we want to find basically. That is nothing but E of Z, right? And the second, if I get tail, let us say, if I get tail, now how many tosses I have? I have wasted my two tosses. Two tosses are gone, right? And additionally, how many tosses I need? It is nothing but, I mean, it's nothing but as if you are starting the game all over again, right? So that's why it is E of Z. This is very, very tricky thing here. You got this, why I have written. I have written this. E of Z is what you want to find. Expected tosses to get two consecutive hits. E of Z is equal to E of Z. Exactly, yeah. E Z is nothing but E of Z. Yeah. Okay, so I hope this is clear, right? And if my first toss is uh, what is this? Is tail, right? How many on an average I will need this thing? If my first toss is tail, so that's it. I wasted my one toss, right? It's like I have to start the game all over again. Right? First toss is gone. Again, I ended up with this thing. Right? This is also clear. That's it. So now we expand the conditional expectation. P times head is the probability of getting head times E of Z given first toss is head. Just Q times E of Z given first toss is tail. P is equal to Q is equal to half for a fair coin. Right? So just substitute that here in this thing and substitute this using this one using this. Simplify it, you end up getting 6. Okay. Yeah, but this is tricky. I mean, today I have only done for only 2 consecutive heads. Next time I'll do for getting k consecutive heads. And yeah, and some patterns, some says some desired pattern as well. So this is one more question, and this we will end today. So what we have done here is we wanted to get two consecutive hits, right? Now I want to get um, one head and one tail. So I'll stop the game if I get one head and one tail, irrespective of the order. That means I'll stop the game if I see if I got tail and head, I'll stop. I'll stop the game if I get head or tail, I'll stop. I'll stop the game if I get T, 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 H, because I have seen T and H. Order is not a problem. That's true. I want just head and tail, that's it. Okay, so again, because it's just two tosses, it makes sense to condition on the first toss. And same E of Z denotes the desired number of tosses as earlier for the desired event. Here it is head and tail. And so first toss is head. If I get tail, I'm assuming fair coin. If I get tail with probability half, I'm done. Two tosses, I'm done. But if I get head, it's like I have to start. Uh, uh, no, I think here I should put here 1 plus E of Z here, right? So yeah, probably here I need to put 1 plus E of Z because I have this. I need not start the game all over again, right? Because I just need the one toss more, right? And then same thing follows here. If my first toss is tail, the same thing follows. I have to adjust this calculations accordingly. Okay, we will do this next week and some more questions with general number of tosses, like 8 tosses. Okay, so I will upload these things and just be mindful of some of the errors I have done. I might have done right while solving these questions. If you have happened to see them, right? Um, okay. Um, Next week, so what I have seen your next week. Let me stop recording.